Hello everyone, I am Pavan Kumar of branch ECE and of roll number 20951A04B7. And today's my topic is the Gaussian maximum likelihood estimator versus the optimally weighted least square estimator. Let's see. Relevance in a system identification and estimation theory, asymptotic covariance matrices are usually used to compare the accuracy of consistent and asymptotically normal parametric estimators for sufficiently large data records. If the data distribution is Gaussian and its mean and variance are independently parameterized, a well-known result is that the asymptotic covariance matrices of the Gaussian MLE and the optimally weighted LSE are equal and coincide with the asymptotic Cram-Error lower bound (CRLB). In the non-Gaussian case, however, as we show in the note, the accuracy of these two estimators may differ. They depend on the parameterization and the shape of the data distribution in the terms of the first four movements. The results are particularly useful when estimating parameters in general semi-parametric models. Now we'll see prerequisites. The lecture notes can be used in courses on system identification, statistically signal processing or estimating theory. The necessary background that has been assumed is similar to the intersection of the prerequisites of those courses. In particular, an exposure to basic probability, stochastic process, and linear algebra is required. Problem statement and solution. The problem is to analyze and compare the asymptotic covariance matrices of the Gaussian MLE and the optimally weighted LSE for general semi-parametric models. Now, here are the some of the models. What is the model? Suppose that model is given yt is equals to mu t of theta plus et of theta, which is t where t equals to 1, 2, or n, where yt is smaller than r, capital R, is a sequence of observed data and denotes the number of available data samples. Theta, which is smaller than equal to r to the power d with a finite positive integer d, is the unknown parameter vector to be estimated, which mu t of theta is a sequence of non-real valued functions of theta, and et of theta is an observed sequence of zero mean independent real valued random variable with the unknown parameter dependent variance denoted as the lambda t of theta. It, that is the for all theta and t, it holds that e of et is equals to 0 and e of e square t of theta which equal to lambda t of theta. Notice that the notice notice that the models does not specify the full distribution of data. Therefore, the model is semi-parametric, where the parameter vector theta jointly parameterizes the mean and variance of data. Let us denote the true parameter as theta. Now the Gaussian case. The Gaussian case. Al- Although the computations in the case of Gaussian data distribution are known as may be found in classical textbooks. For example 5 Appendix 3C. We include them here to highlight the role of the third and fourth order movements of the data distribution when the mean and variance are jointly parameterized. We will also refer back to these computations when considering the non-Gaussian case. Suppose that the true data distribution is Gaussian, and let us first consider the computation of P1 from 2 using the chain rule, it holds that NV1 of theta which equal to sigma t is equals to 1 to n, where minus of t yt minus mu t of theta by lambda t of theta into mu t of theta minus yt minus mu t of theta whole square by 2 lambda square theta into theta into theta t of theta plus 1 by 2 lambda t of theta into lambda t into theta. Differentiating one more time we get, and these are the some of the examples of the given data. Different one more time we get this one, this one, this one, and after that then it holds that this one, and after moreover n square v1 of theta into t which equal to, then we will get this one. Okay, now we are now taking the expectations of both on both sides, and on both sides and using the independence assumption of model we get that this one. And after that, where a alpha t of theta naught is equals to e of my t minus mu t, where theta naught whole cube, and beta t theta naught is equals to e into yt minus mu t into theta naught. And these are the sum of the examples where the sum of three double sums evaluates this one of equation 6, where we now use the assumption that data distribution Gaussian. Under the assumption, the third and fourth order moments are alpha t of theta t is equals to 0, and beta t of theta naught is equals to 3 lambda square theta into theta naught respectively. Then it is straightforward to see that in such a case and expression in 6 reduces, and these are the sum of the, and this is the equation 7 by using the reducing the data, and which is equal to a of v1 mu v1 naught of theta naught, where we include that a p1 equal to, then this after this one is the equation 8, which is equal to the, after equation 8, which is equal to the asymptotic Gaussian CRLB. Notice that here v1 of theta naught is as per the sample Fisher information matrix, and that is it is given as the sum of two terms. The first corresponds to the information from the mean, while the second is due to that from the variance. Next, we compute P2 from 4 using the chain rule. It holds that NV2 of theta is equals to N of t is equals to 1 minus yt minus yt2. And this is the equation 9. After that, moreover, this is the equation. Taking the expectations on both sides using the independence at assumption of the model, and this is the equation. Now using equation 9, it holds that E of v2 of theta 2, and hence we include that p2 is equals to v2 of theta naught, and v2 of theta naught, and after that by comparing equation 8 and equation 10, and noting that the term of 1 by 2 lambda square theta t into theta naught into which is upon into lambda naught t theta naught, which in bracket lambda naught theta naught whole to the power t is a positive. We see that p2 is smaller greater or equal than p1 from Gaussian data distributions. In other words, p2 minus p1 is a positive semi-definite matrix. This result is due to the joint parameterization of the mean and variance. Now conclusion. 1. For Gaussian data distribution where the mean and variance are jointly parameterized, the Gaussian MLE achieves the CRLB and is therefore asymptotically efficient. The optimally weighted LSC, on the other hand, may not be asymptotically efficient. The non-Gaussian case. When I suppose that the true data distribution is non-Gaussian, and let us first consider the computation of P1. Referring back to computations leading to P1 in the Gaussian case, we see the expression in equation 5 is valid in the non-Gaussian case as well. This is because only the independence assumption of the model was required in the computations and not the form of data distribution. On the other hand, the expression in equation 7 is valid only for Gaussian data distributions. Due to specific substitutions used for the third and fourth order movements, therefore in the non-Gaussian case of 7 is not valid. Instead, equation 6 has to be used. Consequently, the non-Gaussian case E, which is E of V naught V001 at the of theta naught and 6 equal to NE of V01 of theta naught into V01 into theta naught is, and the asymptotic covariance matrix in the Gaussian MLE is given by this equation 11. And after that, next we compute P2, referring back to the computations leading to the P2 in the Gaussian case. We see that the expression 10 is valid in the non-Gaussian case as well. This is because higher order movements were not used to be evaluating the expansion, and no assumption was made on the shape of the data distributions. And these are the some of illustrative examples of Gaussian maximums. And what we have learned that the result provided in the previous section show that for the non-Gaussian data distribution with jointly parameterized mean and variance, the Gaussian MLE is not necessarily better than the optimally weighted LSC. We derived the expressions of the asymptotic covariance matrices and established a condition. When theta is more greater than r, under which one of the estimator may be preferred. Finally, using the example, we saw that when the mean and variance are jointly parameterized, the minimum maximum property of the Gaussian distribution may not hold. Thank you giving me for this opportunity.